Math 150, Section 2, Lecture 13, I think. So what we're going to do today is we're going to talk about directional derivatives. We'll talk about applications of directional derivatives. And then we will review some consequences of the chain rule. We'll talk a little bit about how you can use the chain rule to solve a lot of problems which you probably remember the answers from Calc 1, but you may not have seen a good proof, or you may have forgotten the details of the proof. And then as time permits, I will do all of trigonometry in 5 minutes. So I will show you a way to remember all the different formulas from trig. I don't know why the camera likes to move in your section. It doesn't seem to... All right. Oh, someone's phone went off? Whose phone went off? Do you guys choose the pop quiz or the Dunkin' Donuts? The Dunkin' Donuts. Okay, do you understand? Excellent. So there will be donuts or munchkins on Wednesday. Okay. All right, so directional derivatives. So the concept is actually not too bad. So what we're going to do for directional derivatives is we want to find a way to talk about a derivative in an arbitrary direction. So we have a direction v, a point x, and a function f. And what we'll do is we'll look at the limit as h goes to 0 of f of x plus hv minus f of x over h. When you look at this, what might you want to assume about the vector v? So what might you want to assume about the vector v? That's a unit vector, excellent. You definitely want v to be non-zero. If v is 0, we're talking about f of x minus f of x. Okay, that would always be 0. It's not going to be a useful concept. So we often assume that the length of v equals 1. And again, I'm going to put the double lines to remind myself that I'm dealing with a vector. I'm putting the arrows over the x and the v to remind myself that these are things with many coordinates. So we're basically taking a point and we're moving in a certain direction. If v had length 2, well, I could write that as maybe 2 times the unit vector in that direction. If I multiply the denominator by 2 and the numerator by 2, this quantity would then be taking the derivative with respect to a unit vector, but there would be an extra factor of 2 floating outside. So it would really not change what's going on. It would just rescale things. It's often convenient to assume v has length 1. Where have we seen something that looks a lot like this in multivariable calculus? For special choices of v, where have we seen this? So we've seen it before for special choices of v. For those watching at home, it's like we're on an ocean going up and down right now. I have no idea. Partial derivatives. So partial derivatives are a special case. Just take v to be a unit vector in the direction of, say, one of the coordinate axes. So this is just generalizing our notion. If you think back to calculus, to Calc 1, we have the definition of the derivative, which you never, ever want to use in an actual problem. How many of you have ever differentiated the function x to the 1701? Okay. But you could all differentiate x to the 1701. You're not going to look at x plus h to the 1701 minus x to the 1701 divided by h. You will use the power rule. So we take the definition of the derivative, and then we deduce a useful formula for computations. For computations, we never want to use this. We want to use something else. So let's let a of t be f of c of t, where c of t is x of t, y of t. So you could do this for more than one direction. I'm going to just do this right now for the case of 2 dimensions. This is right into me, so I physically override it. All right. So I have over here, here's my point maybe x naught, y naught. When we did the chain rule on Friday, what letter do we use for the inside function? G. We did f of g of. Why am I using the letter C? Yeah, but there's no B.
Because it's a line, but it could be a curve.
It could be a curve. Excellent. It's not because today is my son Cam's birthday, and so I've got C's on my mind. Don't worry, that won't happen when I'm grading the midterms. But I have C on my mind, so I want to use the letter C to honor my son. No. He really wouldn't care. Right? But by using C for curve, that's hopefully reminding us as to what's going on. And let me say that the instantaneous unit vector tangent to the curve, let's call that V, and we'll call its components V1, V2. What I'm now doing is this is going to allow me to calculate the directional derivative. So if we want to write things really explicitly, x of t, y of t is just going to be my initial point, x naught, y naught, plus t times v. And I'll assume v is a unit vector. So if you go in and you do all the substitutions, this is just going to give us the directional derivative. But it's going to give us the directional derivative where we can now use the chain rule to come up with a useful formula and bypass having to take the limit. We do not want to take that limit. Right? Can somebody tell me what is a of t just using Calc 1 results? How would we write that? What's its derivative? Yes? Okay, so it would be f, what? Well, we can't say f prime in multivariable calculus because f is a function of several variables. So what would be the derivative of a? A is a function of one variable, so there we can say a prime. So we can say a prime of t for the left. For the right, we have to use the chain rule. And we get partial f, partial x at the point c of t times partial x, partial t at the point t. That would be the start of the chain rule. The next piece would be partial f, partial y at c of t times dy dt at t. Well, if we think about what's going on, partial x with respect to t. So dx dt at t, that's just x prime of t. Right? X is just a function of one variable. And if we do things at our special point, dx dt at the point 0, that's just v1. Any questions as to how we get here? So this is just the chain rule. And now what is partial x, partial t? Well, that's just x prime of t. And if we want to go at the point t equals 0, that's just v1. That's how we've chosen things. So now when we substitute, what do we get? So we would get a prime of t is going to be df dx at the point x naught, y naught times v1 plus df dy at the point x naught, y naught times v2. Or I can write this as the gradient of f at the point x naught, y naught dotted with the vector v1, v2. And I can just write that as the vector v. So this is a great formula for the directional derivative. It says if you can compute the partials of f, you can find the directional derivative by just taking the dot product. Let's go back and think about where we used these partial derivatives before. When we were doing optimization problems, if I wanted to have a maximum, what must be true for my partials at a maximum? Is there a question? So this means derivative. So we have several notations for this. We sometimes write df, we sometimes write grad f, we sometimes do triangle f. These are all the same, and it just means the vector df dx, df dy. So all of those are equivalent notations. So if we're trying to find a maximum, what must be true about the partial derivatives at my maximum? Sorry? They must be 0. If df dx was positive, if I move in this direction, my function is increasing. If I move in this direction, my function is decreasing. So if I have a maximum, I know partial f, partial x must be 0. Similarly, partial f, partial y must be 0, because if it was not 0, I would be increasing in one direction and decreasing in another. So we use this to get candidate points for maxima and minima. So the candidate points for maxima and minima are going to be the places where the partials vanish. Question? Or?
If that was the length of vector v is greater than 1?
It's equal 1. Equals 1. So we're assuming our vector has unit length. So now, let's look at the directional derivative in the direction of v. What direction v should I choose to make this as large as possible? Where will this be increasing fastest?
Same direction.
In the same direction as what? So what direction v do I take to make this dot product as large as possible?
The same direction as that.
You can't use the word that. That is not allowed. I'm sorry?
What?
Not 1, 1.
Same direction as A of t at that point.
A of t is a number. See, this is why you can't use words like that, because it's not clear what you're referring to. I want to make this dot product the largest as possible. Yes?
Same direction as
So the vector x is my point.
Same direction as gradient f.
The same direction as the gradient of f at the point I care about. I want to make this dot product as large as possible. How do I make this dot product as large as possible? V should be in the same direction as the gradient of f. If it's in the same direction as the gradient, it's maximum reinforcement. Okay, so this is worth isolating. And so what we will be able to do is we can say, if we look at the directional derivative, so directional derivative is increasing fastest when v is in the direction of the gradient of f. So that's the direction I should go to see the maximum possible change in my function. This is giving us an interpretation for what the gradient means. It's pointing in the direction of maximum change. If I wanted things to decrease as rapidly as possible, which direction would I choose? The opposite. So directional derivative is decreasing fastest if v is in the direction of negative gradient of f. So if I'm going in the direction of gradient of f, I'm changing as quickly as possible. If I'm going in the opposite direction, I'm decreasing as fast as possible. What if I'm perpendicular to the gradient of f? Then there's no change. And that's where you get the tangent hyperplane. It's going to be that n-1 dimensional space perpendicular to the gradient. So the gradient is basically the normal to the surface. So grad f is in the direction of the normal to the surface. So maybe I look at all inputs x and y, such that f of xy equals 3,300. Maybe I'm looking at a certain elevation in Williamstown. What are all the points where I'm 3,300 feet above sea level? And then the gradient of f will tell me which direction should I go to see the maximum change. Or I could be looking at the temperature map. Right? So it's nice when we have an interpretation for what these quantities mean. Yes?
Can you say again what did you call it when you're going perpendicular the entire time? Or when the change is 0?
So when the change is 0, you're basically staying in the level set. You're staying in the set of x and y that evaluate to the same thing under f. Because if there's instantaneously no change, that's going to be where your tangent plane is. So the gradient is telling you which direction to go. So if you imagine you have the sphere x squared plus y squared plus z squared equals 1, I can solve for z in terms of x and y, and then we do the hemisphere. I get z. So imagine I have, z is f of xy is the square root of 1 minus x squared minus y squared. So there's my hemisphere. I can calculate the gradient. So let's calculate the gradient of f. All right, so I've got the square root, right? So I first take the partial with respect to x. I have 1 minus x squared minus y squared to the 1/2. So I have 1 minus x squared minus y squared to the negative 1/2. It comes down below. I then take the derivative of this with respect to x, and I'll get negative 2x. I do it very similarly, and I get negative 2y over 1 minus x squared minus y squared square root. So that would be the gradient of f. I can pull out the square root of 1 minus x squared minus y squared. And I get the vector xy. So what this is telling me is, yes, did I make a mistake?
It's the power of 1/2, which you have to multiply by 1/2.
Yes, and I have to multiply by 1/2. Thank you. And so, if you'll notice when I went to this line, I had already dropped the 2, because I know what the answer is. And so I'm saying one thing and writing one thing, but I'm thinking something else. So when the algebra settles, we have some constant times the vector xy. Okay? And so this would basically be giving us the direction. Okay? Now the question is, how do you want to be viewing this? So we have z as a function of x and y, it's the square root. So what does it mean over here? This is where things can get really subtle, and this is nice when we have time to talk about stuff like this. How many directions, how many dimensions is this? 2. How many directions is this object? So if I really want to be talking about the sphere, I should be viewing it as a function of 3 variables, not writing z in terms of the other 2. I can still calculate, and I can still do all this formally, but it's a slightly different object. It is really easy to make these small, subtle mistakes in terms of what you're looking at. If I want to look at the sphere, I could look at the function, I use a different letter. G of x, y, z is x squared plus y squared plus z squared equals 1. This is going to be the set of all points that are on the unit sphere. Now if I take the gradient of g, this is going to be 2x, 2y, 2z, or just 2 x, y, z. So if you think about what's going on now, here is a plot in 3-dimensional space of the level set g of x, y, z equals 1. It's the set of all points that evaluate to 1 under g. I now calculate the gradient. The gradient is the point of maximum change. And what it's telling you is, if you want to look at where the function x squared plus y squared plus z squared is changing the most, just go normal to the surface. And that, because this is the same direction as the radius. This is the same direction as the point x, y, z. If you're on the surface of the sphere, here's 0, here's the point x, y, z. So it's telling you, just keep going in that direction. And that will be the direction of maximum change. The direction of minimum change would just be going in any direction perpendicular to that. You'll basically be staying on the sphere. So if you want to leave the sphere, you want to go off in that direction. So the sphere is very nice geometrically to see what's going on, to see the direction we want to move. So there is an interpretation. But you've got to be very careful because we often write one variable in terms of the other. We can write and represent things many different ways. And the different approaches have their pluses and minuses. If I'm talking about a 3-dimensional space and I want a 3-dimensional vector, this first approach is not giving me a 3-dimensional vector. It's giving me something 2-dimensional. You can still talk about what that gradient means, but it's not exactly the problem we were looking at. So here, the big takeaway is the directional derivative tells you the direction of the maximum change. So if you want to think back to the optimization, we now have the following. So directional derivative, gradient of f dotted with v. If I'm at a maximum, what should be true about the directional derivative? So yes. Well, so if the gradient is in the same direction, if my vector is in the same direction as the gradient, this is going to be as large as possible. Will I be at a maximum? So this is telling me how much I change in the direction of v. So you've just given me the direction where I have maximum change. So if I want to be at a maximum, what should be true no matter what direction I walk? What should I see? Will my function be getting larger in any direction? If the gradient wasn't 0, choose v to be in the same direction as the gradient, and you'll find a direction to go and make it larger. Take v in the opposite direction, you'll make it smaller. So there's no way you could be at a maximum or minimum if the gradient is non-zero. So this is another way to see df dx df dy must be 0 at a critical point. I mean, it must be 0 at a maximum or minimum. If grad f is not 0, cannot be a max or a minimum. Now, unfortunately, if it's 0, that is not enough to prove that you have a maximum or minimum. It just gives you the candidates. So we have a really nice test for candidates. Is the gradient 0? If yes, great. If not, we know it's not a maximum. Just choose v in the direction of the gradient of f, and you'll get larger. Choose v in the opposite direction, and you'll get smaller. Okay, yes. Okay, any questions about the gradient and directional derivatives? So now the way you calculate a gradient, you know how to do that. You know how to do a dot product. So if I ask you, calculate a directional derivative of a function in a direction, you just calculate the gradient and do the dot product. So it's now just using techniques you've already seen before. All right, what I want to do now is talk very briefly about the inverse and implicit function theorems. These are two very big results which we are not going to really cover. You should at least have heard that they exist. If you take real analysis, there's a good chance you will see them in greater detail. The idea is, when can you write one function in terms of another? So if I give you y as a function of x, can you write x as a function of y? So inverse function. So imagine I give you y equals x squared. So again, the difference between a function and a relation is, for a function, if I give you an input, there is a unique output. If I asked you, what class are you taking at 9:24 on Monday? There should be a unique answer. You should not be taking multiple classes that meet at the same time. If I ask you, what's your favorite, what sports teams do you like? What colleges do you hate? That can be multiply defined. You can have many teams that you like. Okay? I'm seeing some people shake their head. You can have many teams that you like, or at least some people can. Right? Is this a function? If I give you a value of x, is there a unique value of y? Yes. And this is often called the vertical line test. You give me an x, and there's a unique y. So vertical line test. It will test. To go the other way, it's the horizontal line test. If I give you a value of y, is there a unique value of x? So for this function, what's the answer? No. So it failed the horizontal line test. So given a value of y, there's actually two values of x that correspond to it in general. There's a way to fix this. We could say restrict to x greater than equal to 0. And if we restrict to x greater than equal to 0, then it does have an inverse function. X would be the square root of y. And so the inverse and implicit functions, the inverse function theorem is basically, when can you invert? And the condition is, if the first derivative is non-zero, you can invert locally. And you can see that the issue here is the first derivative vanishes, we have trouble. If the first derivative is not 0 in a small neighborhood, what do you look like? If the first derivative is not 0, what do you look like in a small neighborhood at that point? What shape? It looks like a straight line. A straight line's invertible. You're not exactly a straight line, but the deviations are so small that you can invert. And essentially what the inverse function theorem says is, if the first derivative is non-zero in a small neighborhood, if I can write y in terms of x, I can write x in terms of y. So we're not going to really cover that in great detail, but it's worth knowing that something like this exists. What I want to do now is I want to shift to applications of the chain rule. So I'm going to use this to derive things you have hopefully seen in a previous calculus class. You may have forgotten them, and you may not have actually ever seen a proof of them. So, applications of the chain rule. So imagine a beautiful pure functions f of g, such that f of g of x is x. We sometimes call this the identity function, the do-nothing function, the Seinfeld function. If any of you who still remember that TV show. What's the net effect of applying g and then applying f? You return to where you start. The output is the same as the input. Okay? So if a of x equals x, what's a prime? So if a of x equals x, what would a prime be? It would just be 1. So we get a prime of x, because it equals x, it's just going to be 1. But it's also going to be f prime at g of x times g prime of x by the chain rule. So this allows us to solve for g prime in terms of f prime. So we get g prime of x equals 1 over f prime of g of x if f of g of x equals 1. So this is an incredibly useful relationship. If you know the derivative of f, you know the derivative of f's inverse function. So for instance, if you've seen the exponential function, we can use this to calculate the derivative of the inverse exponential function. What is the inverse exponential function? What function undoes exponentiation? Log, natural log. So let's recall the exponential function. So we can write it as x, sometimes we write it as x of x, and it's 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus yada yada yada. It's the sum, and it goes from 0 to infinity of x to the n over n factorial. We will do a lot more with this later in the semester when we get to sequences and series. I'm just trying to get a couple things on your radar screen now. The more times you see some of these things, the better it's going to be. Okay. You've seen this definition of e to the x. This question I really would like people to answer. How many of you have seen this as the definition of e to the x? How many of you have seen the derivative of e to the x as e to the x? Wow. So, for those of you who are raising your hands, if you've seen the derivative of e to the x as e to the x, how do they define the exponential function? Oh dear, okay. So this is an opportunity, I guess, to talk to you about the exponential function. Sometimes you see it through compound interest. E to the x is defined as the limit as n goes to infinity of 1 plus x over n times n. I'm really not going to go through this. This is the compound interest approach. You are compounding at a rate of x percent per year, compounded instantaneously. Right? We will not do this. It is equivalent to the series expansion. How do you think we should take the derivative of this infinite sum? What should the derivative of a sum be? Sum of the derivatives. So this is physics hat or engineering hat day, where you just use results without bothering to see if they're true. So let's just take the derivative term by term. What's the derivative of 1? What's the derivative of x? Derivative of x squared over 2 factorial. 2x over 2 factorial. What's the derivative of x cubed over 3 factorial? 3x squared over 3 factorial plus 4x cubed over 4 factorial. And now when the dust settles, the 2 cancels and you get x. The 3 cancels one of the 3's and you get plus x squared over 2 factorial plus x cubed over 3 factorial. And what does this equal? E to the x. Unfortunately, this is not a proof. This is assuming that the derivative of an infinite sum is the infinite sum of the derivatives. It is true in this case because n factorial grows so rapidly you can justify all of this. But you do not know that fact. I will show you in a few moments that the derivative of a finite sum is the finite sum of the derivatives. You have probably only done the derivative of a sum of 2 terms is the sum of the 2 derivatives. It turns out it's not bad to expand that. What is e squared times e cubed? It's supposed to be e to the 5th. I love how you said supposed to be. So in general, if I give you e to the x times e to the y, what this means is the infinite sum of x to the n over n factorial times the infinite sum of y to the m over m factorial. And then after you use the binomial theorem, and we'll probably do this later in the semester, and the dust settles, you get x plus y to the k over k factorial, which is e to the x plus y. This has to be proven. You cannot just assume. We have horrible notation at times in math. We are the makers of cosecant is related to 1 over sine. It would be horrible if e squared times e cubed is not e to the 5th. This notation would suck. We have a history of bad notation. You need to prove this. It can be proved, fortunately. The notation actually does work out. It is good here. But it really means a statement about infinite sums. Let me show you that a derivative of finite sum is the finite sum of the derivatives. This uses one of my favorite proof techniques. So it's proof by grouping or by parentheses, whichever you prefer. Right? So imagine I want to calculate the derivative of f plus g plus h. So I want to calculate the derivative of 3 terms. We never proved in Calc 1 that the derivative of 3 terms is the sum of the 3 derivatives. We proved it for the sum of 2 terms. So what I will do is I will group the first 2 together as f of x plus g of x plus h of x. Now I have the derivative of a sum of 2 functions. I can now use the result from Calc 1. What's that going to be? It's now just going to be f of x plus g of x plus h prime of x. How do I take the derivative of f plus g? What can I use to take the derivative of f plus g? It's just what I've been using. I'm assuming I know the derivative of a sum of 2 terms is the sum of the 2 derivatives. I can now use that right here. And I would now get, this is just f prime of x plus g prime of x plus h prime of x. So still in parentheses. And now I can drop the parentheses because addition is commutative, and I get f prime of x plus g prime of x plus h prime of x. So you can do this for any finite sum. But you can't necessarily do it for an infinite. Something has to be justified there. The problem becomes a little bit harder. In the first section, somebody made a good comment about, is this similar to Newton's method? We had a sequence of things converging to a root. And if you want, you can look at it as you're taking more and more terms in your formula for e to the x, getting a better and better approximation. At any finite collection, we can use this result. And then you just somehow argue that it will hold in the infinite limit. But it is something that must be proven. Okay? So again, first year, how many of you have this as your first college math class? Okay. First college math class is in some sense the hardest, because you're all coming from different backgrounds, and some of you will have seen things and others of you will not. By the end of the first class, hopefully you're now all on a similar place in terms of what you've seen, what you haven't seen. All right. What I want to do now is I want to look at applications of the chain rule. So we have, if f of g of x, this should be not equals 1 equals x, then g prime is 1 over f prime at g of x. We're going to use this to calculate some derivatives. So we were talking about the exponential function here. And you mentioned that the inverse of the exponential function is just the natural logarithm. And this is almost proof by words. So if I look at exponential of natural log of x, this is raising e to the natural log of x. What does the natural log of x mean? It's the number of powers of e I need to get x. So I raise e by the number of powers of e I need to get x. What should I get? X. So these are my inverse functions. I will now just write this as f of g of x. I feel like I'm making a Broadway billet. The role of f today will be played by exponential. The role of g today will be played by logarithm. Right? We just substitute. We now have a formula. G prime of x is 1 over f prime of g of x. Okay, so that means the derivative of the natural log is just 1 over... Okay, what's the derivative of the exponential function? What's the derivative of the exponential function? E to the x. It's itself. It's the exponential function at g of x, which is the natural log of x. Oh, that's just 1 over x. And so this is a proof that the derivative of the natural log is 1 over x. If we know the derivative of the exponential function is the exponential function. How many of you have seen this as the proof of the derivative of the natural log? Have any of you seen this as the proof of the derivative of the natural log? I'm sorry?
I'll show you my directions and stuff.
Okay. So, how many of you know the derivative of the natural log, or knew before today the derivative of the natural log is 1 over x? How did you know that? I see. So this is the Moses method of mathematics, where he comes down from Mount Sinai with commandments from thy Lord. And this is the set of 5 tablets that were smashed in his anger.
Right? We didn't need another proof.
Didn't right. Well, at least it's good to see where they are. I'll note the following. Change of basis formula. The log of x base b is the log of x base c over the log of b base c. The power of this is if you know logarithms in one base, you know them in another base. If you take c equals e, this gives you the derivative of the log of x base b is the derivative of the natural log of x over the natural log of b. I don't use the quotient rule. This is just the constant rule. 1 over log b is a constant. And you just get 1 over x times the natural log of b. So this is how you would get the derivative of logarithms in other bases. Okay? If you want to calculate the derivative of b to the x, I leave that as an exercise. Okay? Any questions on logarithm? All right. About 10 and a half minutes, 2 topics to go. It's going to be tight, but I think we're going to get there. I want to make sure we can do trig in a day. Let's do arctangent. I want to calculate the derivative of arctangent. I need a function which, when I evaluate it at arctangent, I get x. Does anybody know a function which, when you evaluate it at arctangent, you get x? Tangent, right? The tangent of the angle whose tangent is x is x. Again, these are proof by word. So we get the derivative of arctangent is just 1 over the derivative of tangent at arctangent of x. Anybody remember the derivative of tangent? Yes? Secant squared. If you forget, you write tangent as sine over cosine and use the quotient rule. And when the dust settles, you get the derivative of tangent is secant squared. Secant is 1 over cosine, because math notation often sucks. So you get 1 over secant squared. Secant is 1 over cosine squared. So you get the derivative of arctangent of x is cosine squared of arctangent of x. This is not a pleasant function to look at, but it's going to simplify beautifully, and it allows me to illustrate some really good techniques. Draw a picture. I'm dealing with right triangles, so let's have some angle here. Theta is the arctangent of x. So I want to draw a right triangle where this angle has a tangent of x. Which should I choose the opposite side to be? What should I choose the adjacent side to be to force the tangent to be x? You have infinitely many choices. What would be a good choice? I want the tangent of this angle to be x. What should this side be? So tangent is opposite over adjacent. Yes?
X squared.
If I choose this to be x squared, what do I want this to be down here? X. So rather than doing x squared and x, x and 1. So if I choose this to be my triangle, I'm forcing the tangent to be x. By Pythagoras, the hypotenuse is the square root of 1 plus x squared. We can now calculate the cosine of theta. The cosine of theta is just 1 over the square root of 1 plus x squared. So when I settle this and the dust goes through, it's just 1 over 1 plus x squared. That's a really nice function. That's much better than the square of the cosine of the arctangent of x. So a lot of times you can simplify ghastly expressions. So when we drew the picture, we wanted to draw a really good picture where we want an angle whose tangent is x. And so now we can actually calculate, if you wanted to calculate the derivative of arc sine, you could do that. All right. So we've got a little bit over 5 minutes left. This is enough time to do all of trig. So how many of you remember your trig angle addition formulas? The sine of x plus y and the cosine of x plus y. Okay, I see a small number of hands going up. These are often forgotten. They are extremely important. I want to give you a sense of why they're true, as well as how to remember them. So again, if the electromagnetic pulse is detonated over America and all of our electronics are fried, and somehow you need to know these, you will be able to get them. Right. Sine of x plus y is sine x cosine y plus cosine x sine y. Cosine x plus y is cosine x cosine y minus sine x sine y. Here is a proof, at least if the angles are small. Here's x, here's y. If I come down straight like that, this is going to be the sine of x plus y. I am now going to keep drawing right triangles. Right triangles make me happy, because I can keep using Pythagoras. So if I draw this right triangle, the hypotenuse here is 1, the angle here is y, so this diagonal line here would just be the sine of y. This hypotenuse up to here would be the cosine of y. So if I then wanted to calculate this vertical height here, this would be the cosine of y times the sine of x. And that would give me this vertical height. If I now go over horizontally like this, the sine of x plus y would be the distance from here to here plus the distance from here to here. Okay, well, this distance is the same as that distance. If this angle is x, then this angle would be x over here. So this would be 90 minus x, so this would be x over here. So this length would be the cosine of x times the hypotenuse. So this length over here would be cosine x sine y. And that's going to be my formula for the sine of x plus y. Cosine x sine y plus cosine y sine x. Okay, so I've got them in opposite orders, just put them together. Right? That is a geometric proof if the angles are small. I'm now going to give you a way to derive all of them. So I'm going to start with e to the I theta is cosine theta plus I sine theta. And similar, e to the minus I theta is going to be cosine theta minus I sine theta. And the reason is if you replace theta with negative theta, the cosine of theta and cosine of negative theta, they're the same because cosine is even. The sine of negative theta is negative sine of theta because sine is odd. So we just showed earlier that e to the z is 1 plus z squared, plus z plus z squared over 2 factorial plus dot, dot, dot. Yes? Did I make a mistake?
No, so why is the I only in front of the sign and not?
That's just how it turns out to be. And here, I equals the square root of negative 1. So I'm going to try to give you a sense right now as to why this is true. So this is the formula for e to the z. Later in the semester, we will find the formula for cosine of z. And that's 1 minus z squared over 2 factorial plus z to the 4th over 4 factorial minus dot, dot, dot. The sine of z is z minus z cubed over 3 factorial plus z to the 5th over 5 factorial minus. So these are called Taylor series. These are representing a complicated function in terms of an infinite sum. And if you look at what goes on, if you look at e to the ix, that's going to be 1 plus ix squared over 2 factorial plus ix cubed over 3 factorial. Whenever I have a term with an even power, well, I squared is negative 1. So I to an even power is either going to be 1 or negative 1. Whenever I have a term with an odd power, I'm either going to have I or minus I. And when the dust settles, if I plug this in, this is going to be, if I put all the even terms together, I'm going to get cosine of x plus I sine of x. Another way to just briefly see what's going on is if I draw the unit circle, here's the point e to the I theta. This is the point cosine theta, sine theta. We write this as cosine theta plus I sine theta. So this is using complex numbers. This is the x direction, and this is the I times y direction. I'm being a little bit cavalier in terms of the proof of this. I'm just trying to give you some sense as to why this is true. We will talk more about this when we get to Taylor series later. All right, so now e to the I theta times e to the minus I theta. That's e to the what power? E to the 0, and e to the 0 is 1. So this is cosine theta plus I sine theta. Cosine theta minus I sine theta equals 1. So I get cosine squared theta, cross terms cancel because of the minus sign, minus I squared sine squared theta equals 1. But what does I squared equal? 1. Negative 1. So negative I squared is 1, so we get cosine squared theta plus sine squared theta is 1. There's Pythagoras. Sine squared plus cosine squared is 1. Got a little bit over a minute, almost 2 minutes to do all of the trig identities. Not bad. We're in good shape. All right. Let's do the angle addition formulas. So now what I'm going to do is I'm going to look at e to the ix, e to the iy is e to the I x plus y. So what does this become? This becomes cosine x plus I sine x times cosine x plus cosine y plus I sine y is cosine of x plus y plus I sine of x plus y. All right, now when I multiply things out, what's real and what has the imaginary I in it? Cosine times cosine, that's real. My I sine x, cosine y, imaginary. Cosine x, I sine y, imaginary. I sine x, I sine y, real. So let me put all the real stuff together. I'll get cosine x, cosine y. Then I get an I squared, which is a minus 1. So minus sine x, sine y, plus I sine x, cosine y, plus cosine x, sine y. Well, the only way two complex numbers can be equal is the real parts are the same and the imaginary parts are the same. So cosine of x plus y, cosine x, cosine y, minus sine x, sine y. Sine of x plus y, sine x, cosine y, plus cosine x, sine y. The trig identities, they really come from the exponential function. It's hidden, it's not really emphasized earlier in your semester, in your career, but that's what's going on. 4 seconds to spare, not even close.